As best we can tell, the universe has a beginning. The best explanation of that likely fact is that something beyond matter, space, time, and energy brought the universe into existence, and that something has attributes that correspond to those that Jews and Christians or traditional theists have assigned to God. Transcendence, volition, power, and even intelligence when we start to look at the degree to which the universe has to be fine-tuned from the beginning.
Whether they've pieced it all together and applied it to the Penrose model would agree. These are pretty standard critiques that you're making. Dr. Stephen Meyer, welcome back to part 2 of our conversation. It turns out, fascinatingly, that there's a battle that is emerging over the Big Bang, and the preeminent Sir Roger Penrose responded to a video of mine in which I interviewed you. He raised some challenges. In our last video, we talked about why his critique is so important, who he is, kind of where we stand in this debate. We promised we'd come back and do a deep dive specifically responding to his model, because the question is, does the science point towards the universe having a beginning or not? If it does, that cries out, as we both agree, for a supernatural explanation. And he has one of the most preeminent models challenging that the universe had a beginning in the way that we would understand it. We're going to do a little bit of a deep dive, and I'm going to turn the reins over to you. I want our audience to know.
Could be a big mistake, Sean.
No chance.
Yeah.
But I want people to know this might be one you listen to 2 or 3 times, and if you don't get a particular point, see the big picture of it. That's what's most important. But before we dive in, did I miss anything about how we want to frame this conversation?
Well, what you said was perfect, but there's an additional element we should add, and just reminding that your audience that last time we talked about how these new cosmological models, these infinite universe models are possible, but they come at a very high cost, especially to those who hold to philosophical naturalism or materialism. So the basic structure of my argument in Return to the God hypothesis is a kind of either or, pick your poison argument in challenge to scientific materialism. Either the universe has a beginning, and my contention and that of several of my key colleagues is that, and I would say the majority of the physics and cosmology community is that as best we can tell, the universe had a beginning. But I also acknowledge that it's possible to model your way out of that. You can, with very clever mathematical modeling, you can conceive of the universe as being infinite in duration, and make your model consistent with the data, though not, I would say, not motivated by the data. Okay, and so in the first instance, if as best we can tell, the universe has a beginning, the best explanation of that likely fact is that something beyond matter, space, time, and energy brought the universe into existence, and that something has attributes that correspond to those that Jews and Christians or traditional theists have assigned to God. Transcendence, volition, power, and even intelligence when we start to look at the degree to which the universe has to be fine-tuned from the beginning. Alternatively, if you want to say, well, maybe the universe didn't have a beginning, and here's a bunch of models that propose an alternative, my claim is that those models always come at a very high cost, particularly to naturalism. They first come at a high cost to the coherency of physics, that invariably to model the universe as having infinite duration in the past, there's very often times the modelers are having to posit physical properties or processes that have no precedent in our experience or which even violate known principles of physics. They often will involve some level of mathematical sleight of hand, as in Hawking's use of imaginary time, for example.
The idea is that there is a quantum origin of the universe, and imaginary time is a way of approximating the properties of this quantum origin. So that's the proposal that Hartman and Hawking had.
And they almost always involve violations of Occam's razor in the sense that they needlessly multiply new theoretical entities. They have a number of very ad hoc postulations. But finally, and most importantly, every single model that I and my colleagues have looked at involves introducing unexplained new levels, new unexplained fine-tuning, and a great deal of it. And so that new fine-tuning provides support for a different form of theistic argument, the argument from contingency, or the argument a design argument. And so you can get around the cosmological argument, but only at the cost of going right into the teeth of an even stronger fine-tuning argument. And this was actually first illustrated by Einstein when, in the 19-teens, he realized that his theory of general relativity implied the need for an outward pushing force to compensate for gravitation to create empty space in the universe. That outward pushing force he dubbed the cosmological constant. And so far, so good.
Yep.
But then he assigned to the cosmological constant a very precise, in fact, finely tuned by Einstein value in order to depict the universe as being in a kind of balance between the outward push of the cosmological constant and the inward push of gravity. So that was, in a sense, the first cosmological model that illustrates this point we're making. You can get around the evidence for a beginning, but only at the cost of an exquisite and degree of fine-tuning, unexplained fine-tuning that provides grounds for theism, provides other grounds for theism, supports a theistic argument for other reasons. So it's kind of it's either a cosmological or a fine-tuning argument, or both is the situation that the naturalists are confronting.
So either the universe has a beginning, which has theistic implications,
right,
or we maintain an eternal universe, but it takes a mind to do so, fudging with the physics, so to speak, which would also imply theistic implications.
Yes, and it is often the modeler will often introduce the fine tuning and often be somewhat unaware of what they're doing. In Sir Roger's response to my comments in our discussion last time, he said, well, where is this fine-tuning? I don't see, we didn't introduce any, there's no fine-tuning involved.
I have no idea what he's talking about. There isn't any fine-tuning of this sort. The main material in the universe is dark matter, and the dark matter comes about through gravitons. And it's not a question of any fine-tuning. There isn't any fine-tuning in. I don't know what he's talking about.
Well, he didn't calculate any fine-tuning, but he introduced it in order to make his model work. So he modeled the need for fine-tuning and quite a great amount of additional fine-tuning beyond what's already there in our normal discussions of cosmology.
So that distinction between modeling and introducing, if people listening right now are going, I don't understand, well, you're in the exact right place, because that is a part of what we're going to unpack.
We're going to break it down.
You've put together a very careful, thoughtful PowerPoint, and we're not going to read all of that here, but we're going to give a link to it so people can follow, they can study it, they can assess it, see the documentation. We'll have some pictures jump up. But if Sir Roger Penrose watches this and says, you know what, I'm up for a conversation, we would love to host him here at Talbot School of Theology. You agreed to fly back down, or the two of us would fly somewhere to meet with him.
Well, he's in Britain. We would probably allow him to come remotely, I suppose, right?
We would do that in a heartbeat if he wanted to have a conversation.
He's a wonderful scientist and a wonderful man, and I welcome the conversation. And in fairness, we had a very rushed conversation about his model at the end of a rather long discussion of the situation in cosmology and the cosmological argument. So part of the reason we're doing this is so that we can kind of tidy that up a little bit, clean that up, and clarify the points. There are a couple of things that I got wrong, but I think the substance of our critique stands, and we're gonna try to show that this morning.
All right. Well, I'm honored that one of the preeminent scientists of our day cares about what is covered on this podcast and weighed in. So I'm going to turn the reins over to you. I'm only going to jump in now and then, maybe to clarify or ask a question, but take it away.
Well, why don't we start with a discussion of the three great cosmological models of the 20th century. The first was coming into the 1920s with the discovery of the expanding universe. The first idea was the idea of it was now known as the hot Big Bang model, the idea that the universe had a beginning and it has been expanding outward from that beginning. And your audience will see on the screen a depiction of these three models, starting on my far left, the picture of the hot Big Bang, where you have the beginning and the expanding universe outward, sometimes depicted as what's called a light cone. The second model that came along to challenge that was the idea of the steady state, and that was the idea proposed by Fred Hoyle and Herman Bondi, Thomas Gold. I was oddly fortunate enough to meet all three of those men at different points in my young career. But in any case, their idea was that, yes, the universe is expanding, but there is but it's been always expanding. And there's a force that Hoyle called the creation force, that as the universe expands and stretches, because there is in his view, he postulated that there was a need for constant density in the universe. This was a pure theoretical postulate, but he proposed this, that then as the universe expands, then new matter must be created to maintain that constant density. And so it would kind of pop into existence. So he attempted to account for the expansion of the universe, but within an infinite universe cosmology. Okay?
No beginning point.
No beginning point. It's expanding now, but it's always been expanding. It's getting bigger now, but it's always been getting bigger. And but what's remaining constant is the amount of matter per unit volume, its density.
Gotcha.
That model came in for hard times, in particular with the discovery of the cosmic background radiation, which was a direct prediction or something that was expected on the basis of the Big Bang, but was not expected on the basis of the steady state. Steady state never envisioned a place where all the matter in the universe would be congealed into one place. Rather, it was popping into existence in little localized areas all the time. So by the 1960s, pretty much all physicists, mid-1960s, steady state kind of goes by the boards. Hoyle holds on for a while, maybe all the way to the end of his life, but the model did not. In the 70s and 80s, another model came about, and this kind of illustrates the way you can model your way out of what seems to be the prima facie implications of cosmological or astrophysical evidence. So again, have to account for the expanding universe. And so the oscillating universe, and this is the third picture, this is one on the far right, the oscillating universe suggests that the universe is expanding now and then collapsing.
In a crunch.
Into a crunch, but then it will bounce and expand again and recollapse ad infinitum. So yes, we're in an expansion, but it's only one of an infinite number of expansions and contractions. That model ran into a couple of problems. First, empirically, was determined that there wasn't enough matter in the universe to cause a gravitational recollapse, even taking into account dark matter. And secondly, even a more fundamental concern was the realization, this was something Alan Guth showed at MIT in the 80s, that with each successive cycle, there would be less and less and less energy available to do work. So if you think of a ball bouncing, it will bounce and bounce and bounce. The total mass energy of the system, when you consider everything around the ball, is the same, but the energy available for the ball to have another bounce is going to dissipate with each cycle.
So the equivalent of a hand that's pushing it down, the universe wouldn't have such a hand.
Yeah, exactly. and there were other problems with this model as well, but this idea of the buildup of entropy, disorder, a disorderly arrangement of matter means less energy available to do work, to cause something good in the next cycle. And so it also, if there's a finite number of cycles, there must have been a beginning to the universe. All right. So this is essentially where Sir Roger's model comes in, because he's trying to solve this problem of the buildup of entropy, where entropy is essentially disorder and a loss of energy available to do work. And so he has a kind of 5 or 6 step scenario whereby he attempts to solve that problem and to depict the universe. Now I have another picture that your audience will see here. It's the second one up, and this is from a 2018 paper that he wrote. And this is one of the things I got slightly wrong in our discussion.
Penrose wrote.
Yes, that Penrose wrote. This is our second, the second picture here, and it shows a series of big bangs and expansions of the universe, followed by a new Big Bang and a new expansion. So it's not like the oscillating universe where it goes big, small, big, small. It goes big, and then gets bigger, although there's a twist in all this, in that he rescales or resizes the universe at each what he calls a crossover event, where you move from one eon of cosmic expansion into the other. The picture is slightly misleading. I got it from, it was in his 2018 paper, but he later acknowledged that it didn't quite capture the model.
Okay.
And that's understandable because it's kind of hard to envision the model.
Sure.
I
Sure.
took, in our conversation, this picture a bit too literally, and this was a mistake I made. The new universe and the new eon does not come out of a patch of the old universe. It comes out of the whole thing, where the whole of the universe has been rescaled or resized from big to small. The sense you get is that you have an expansion, and then there's out of somewhere in that existing universe, there's a patch of that universe.
That's just plain wrong. The next eon just describes the whole universe, and it comes from the whole universe previously. There's no little patch anywhere in it. That's not part of the story.
Maybe he kind of watched this video that we had, that there is a little patch that comes up, because that's the only reference to a little patch that I know of. And of course, our video is just, I think, an animation. We shouldn't take it too seriously in that sense, because really the entire universe maps to the entire universe. In all versions of CCC, it's the entire universe that maps to the entire universe. It's just that it loses a sense of a scale, or is this what Roger calls conformal rescaling, because the theory becomes scale-free at some point in the far future and near the Big Bang.
It's a little mind-blowing and mind-bending, but that's what's meant by conformal cyclic cosmology. The conformal resizing is something we'll explain, okay? But that's in a sense one of the essential elements of his model, okay? So now if we if we keep in mind that problem of we've got at the end of the expansion of this universe, we've got a very big, cold, dark, disordered universe. Disordered in the sense that the matter and energy is very diffuse and it's not any longer available to do work. And so if you're going to get a new expansion phase, you're going to have to somehow get that, reduce that entropy, that disorder, make it more orderly, and therefore create the conditions for doing work, okay? So that's the problem he's trying to solve, essentially. So he does it in several steps, and I'm available to stop talking and let you clarify anything. Are we okay
great.
so far?
So are we on to a multiverse scenario? Because the first three are one universe that's oscillating or steady state?
I would say, I mean, you could think of it that way, but I would say, no, this is not really a classic multiverse model.
Okay.
These are all, multiverses are causally disconnected from each other, and they're really separate in that sense. These are different eons of expansion that are all connected in a series going back infinitely into the past and continuing infinitely into the future. That's the model. So now notice, again, his model, like all the other models we've seen before, is consistent with the idea of the galaxies moving away from us, as indicated by, we talked last time about the red shift data, the way in which the light coming from distant galaxies is stretched out.
Yep.
Okay, so we've got data showing that galaxies are moving outward in a way, the universe is expanding. He's capturing that in this model because he's saying, look, in our present universe, that's what's happening, and it's going to happen again and again and again, but there's going to be this way in which the universe is going to be resized so that it can start that cosmic expansion over again. It doesn't kind of goes big, small, but it's not the same way as the oscillating universe.
Okay, fair enough. Let's
jump in. So the idea is that at the end of a period of cosmic expansion, Penrose envisions that all the black holes that are in the universe, and black holes being dense concentrations of matter, so dense that not even light can get out of them, okay? The black holes would have evaporated by a process known as Hawking radiation.
Stephen Hawking's discovery that black holes evaporate.
That's where all the entropy goes into the black holes.
So I don't know how deep to go into this, but Hawking radiation is the idea that you've got these virtual particles that form, one with negative energy, one with positive energy, and the one with the negative energy gets absorbed into the black hole, and the one with the positive energy then escapes and goes out into the universe. And as this process goes on, then the black hole is going to start to lose mass, and it will eventually evaporate, okay? And Penrose maintains that as a result of this process, not only the entropy of the black hole, but the entropy of the entire universe will reduce, and that there will be a loss of information, that this process destroys the information about the internal state of the black hole and therefore reduces entropy of the black hole, reduces the disorder of the black hole and of the entire universe. Now, there's a reason he wants to get rid of the mass, and we'll get to that, the mass of the black hole. And he's going to have another process he invokes to do that. But this is actually a quite contentious proposition among physicists. Physicists accept that Hawking radiation would reduce the entropy, the disorder of the black hole, okay? But they don't accept that it would reduce the entropy of the universe as a whole, or that it would destroy the information about the internal state of the black hole. So, okay, what's the big picture here? The big picture is that the Hawking radiation mechanism is getting rid of the mass of the black hole little by little, and in the process, Penrose says, reducing the entropy of the universe, which is what he wants, right? Because you want to get to a low entropy state, which is capable of doing work. All right.
Gotcha.
Okay, so that's the first step, but this is highly controversial among other physicists, quantum physicists. It violates something called the unitary principle of quantum mechanics that affirms that information is conserved, not lost. Okay, and so it's a big deal to violate that. And so this is a contentious proposition, but there is debate about this. Okay.
Okay.
All right.
Fair enough.
So
fair enough.
Okay, that's the first part. That's the first step. And in the PowerPoint, we will have quotes from Sir Roger showing from his, in particular, from a 2018 article, and then a later one he co-authored in 2025, showing that we're representing his view accurately. I always taught my students Bob Dylan, which is most important quote from Bob Dylan: "You can't criticize what you don't understand." Right?
Love it.
So we're going to
simple yet profound.
Okay. All right. So we want no straw men here.
Good.
And okay. So now the second step in Penrose's model, and again his model is called the Conformal Cyclic Cosmology. That was one of the mistakes I made. I called it the cyclic conformal cosmology. I reversed the two terms. And Phil Halper, who interviewed him, was I've debated Phil, so we've got a little history here, and he's a good guy, but he got a little snide about that, condescending.
What that something was, in Penrose's view, is a cyclic model, and that's what Meyer is now attacking. But can he even get the name of the model he criticizes correct?
The Penrose Cyclic Conformal Cosmology model is its formal name, the CCC.
It's not quite right. It's Conformal Cyclic Cosmology. They both begin with C, don't they?
Now, that's not too bad. We all make mistakes. But what's worse is when Meyer describes how CCC actually works.
Okay, Phil,
fair enough.
Phil, simple mistake. Switch the two C's there. So it's the Conformal Cyclic Cosmology. Now, here's the second step. That you've got all the matter that's bunched into the black holes, but there's a lot of other matter in the universe. Okay, and again, we're talking about at the end of a cosmic cycle when you've got things are really diffuse, very disordered, no energy available to work. And Penrose says, well, now what about all the rest of the matter? How are we going to get rid of that? And we'll get to why he wants to get rid of the matter in a minute. But you got to get rid of the matter to do the trick he's going to do. And the remaining matter, he says, is going to disappear as a result of radiation. That he asserts that all other particles of mass will eventually decay by radiation. And this is sometimes called the mass fade-out hypothesis. Okay. And the problem with this is that the standard model of particle physics provides no basis for saying that all matter will be converted into radiation. In fact, in the case of electrons, we know that there's no known or even hypothesized mechanism by which electrons could decay into radiation in this way. So this is a pure postulation. It's pure posit that this would happen with no empirical basis. And so that's also contentious. But you're going to see, the audience will see now in the next step why he's doing this, because you got to get rid of the matter in order to resize the universe. Then this is the third thing. Once mass disappears, there's no longer a scale for measuring length.
But a brief summary of CCC is that it says that with no mass in the early or late universe, there's no way to build a ruler or a clock. So there's no scale, and big and small become equivalent.
Okay, now this is in other words, and then the universe can be treated as if it were very small. There's a little bit of, I'm going to critique this and say there's a bit of mathematical sleight of hand. So if you're immediately saying, wait, that doesn't seem to follow, you're not wrong. You're not off with that intuition. This is something, but Penrose claims this is justified by something called conformal geometry. So let's break this down a little bit. First part of this to understand this is that mass in quantum mechanics or in physics generally defines an intrinsic length scale that acts as a kind of ruler in the universe. There's something called the Compton wavelength that defines a sort of minimal length by which you can measure everything else in the universe, and it's that wavelength, that Compton wavelength, is it's expressed as an equation. It's the Planck constant divided by the mass of the particle in question times the speed of light. And so then you get a kind of, for every particle, there's a corresponding minimal length measure that goes with it. And so if you have mass, you have a kind of built-in ruler that can be computed with this Compton wavelength. That's the sort of idea. Okay. If you get rid of the mass, you can't compute the Compton wavelength. All right? And so you've lost your ruler for measuring the universe for corresponding to each particle, the kind of the smallest unit of length corresponding to each elementary particle. So you lose those rulers, all right? Now, Penrose then claims that the absence of mass eliminates this by eliminating this intrinsic measure of length. He then says that allows for what's called conformal rescaling. Okay, a little heavy here, but let me give it a go, okay?
Give it a shot.
So in a conformally rescalable, or what's called a conformally invariant system, one can change the length of something without changing angular relationships. So imagine an isosceles triangle. You could shrink all the length, but you get no matter how big it is in size, you're not going to change the relationship between the angles. They're all going to be 60 degrees at each one of the three angles.
So just the scale is what changed, not the ratio.
Right. You could have you have a big elephant, a little elephant. The shape is going to remain the same, irrespective of changes in size. Okay. So that's a conformal rescalable, conformally invariant system. So he then further claims that if the universe is conformally invariant, and he says it is now because you've lost your length scale, that would justify treating the universe as if it were very small.
But a brief summary of CCC is that it says that with no mass in the early or late universe, there's no way to build a ruler or a clock. But there's no scale, and big and small become equivalent. Switching to this scale-free or conformal geometry removes the singularity, and according to Penrose, implies a series of cyclic eons where the universe forgets how big it is. In a related periodic time cosmology developed by Afshordy and Gould, the same thing happens, but the future and the past are glued to each other to form a loop. Both use conformal rescaling, and it's this that our intelligent design guru Meyer seems not to understand.
My view is that the Big Bang was something that you can explain by conformal geometry. In conformal geometry, the Big Bang was nice and smooth, and it joined onto something else nice and smooth, which was the remote future of a previous cosmological eon.
Okay. Now, you got to chew on that a little bit to see if you buy that. And I will tell you that most physicists don't. Okay. So it isn't just the guys like Bill Craig or me or others making cosmological arguments. This is highly contentious now within physics. And in the PowerPoint, we'll have a couple slides with Penrose describing this move. Okay, so people can be sure we're representing him right. Good. So, but here's our basic critique of this, and I think most people will follow this. The universe, here's the first point. The universe does not become small simply because we no longer have a way of measuring it. Okay?
Makes sense.
Or because we have performed, more precisely, a mathematical transformation that obscures the reality of length of the object under investigation. Okay, in this case, that object would be the universe as a whole. Okay, so just because we can't measure it doesn't mean that it itself has become smaller. All right, here's an illustration. Let's say we think it's very hard to hike to the top of Mount Everest. It's 31,000 whatever feet. Okay, but let's say we're going to rescale Mount Everest. We're going to say it's not 31,000 feet tall. It's one mountaineering unit. Oh, that's so much easier. Just one unit. It's pretty small now.
Gotcha.
Okay, so this is you're a philosopher. This is an epistemology ontology problem.
Great.
Okay?
That's really helpful.
Okay, so epistemology is the study of how we know what we know. It involves how we describe things, how we depict things. It's our knowledge of something or the way we represent something. And we're confusing our representation of something with the reality, the ontology of the something, okay?
Good.
Now, there's an even more precise critique that comes out of a deep understanding of conformal cosmology, and I'm going to just say it and see if it makes sense, okay? And I'm going to read this to get this right. I crafted this. But in conformally invariant systems, one can change length without changing angular relationships. Think that isosceles triangle, right? Okay. But it doesn't follow that one can change length without changing length. Because when you change the length, you've changed the length, okay? So, and therefore overall size, even if one doesn't have a way of measuring. So just because something is conformally invariant doesn't mean you can arbitrarily assign a new length or size to the system without having to actually change the size of the system. And Sir Roger does nothing to change the size of the universe. He's only changing the way we're describing the size of the universe.
And his model depends upon the universe's size itself changing. That's a necessary component.
It's a necessary condition of getting that new
eon or
a new eon of expansion after what he calls crossover. And I'm going to now the next step in his scenario will make that even more clear why that's the case.
Okay, good.
Okay, so this is the fourth step in his scenario. In the PowerPoint that people will see, I have 6 assertions. Of his model.
And it sounds like as you start this one, for each one, there's an assertion he
assertion.
recognizes that's built in.
Right.
And you're contesting each one of these assertions, or at least saying a lot of scientists contest
Maybe
them.
less so in the very first case, although there's plenty of physicists that would contest, but what second, third, fourth, fifth, sixth, it all gets very contentious.
Okay, good.
Or in the case of the sixth, the final one, you'll see that if it's true, it has theistic implications.
All right, good.
All right?
I can't wait.
All right, now, so here's the fourth one. Once the universe can be treated or rescaled as being very small, the available energy to do work in the universe will appear to be very large. Okay, now here's why.
Okay.
According to quantum mechanics, the amount of energy associated with a particle is inversely proportional to its wavelength. So if the wavelength is small, the energy is high, is higher. If the energy, and the converse is true. So if the universe now can be treated as if it's very small, the wavelengths associated with the remaining radiant energy will be much shorter. They will be effectively not red shifted, stretched out, longer wavelengths, they'll be blue shifted, okay? So this implies that then the amount of energy associated with the remaining radiation will be much greater in this new, effectively smaller universe. This universe we're treating as small. So if we treat it as small, we can also treat it as having more energy available to do work. And now we're solving that buildup of entropy problem. Now this is why, and this is why getting rid of the mass is so important, because this conformal rescaling that he does will only work if there's no mass. You've got to get rid of, to have even, to make this even remotely plausible, you've got to get rid of the intrinsic length scale, the intrinsic ruler, and that's dependent on the existence of mass. The mass. So if he gets rid of the mass, he can rescale. If he can rescale, he can treat the universe as effectively very small. If it's effectively very small, the energy is effectively
you have more energy
available to do work.
Got it.
Okay.
That makes sense.
All right.
Okay.
So
Tracking.
so there's that's
Yep.
step 4 or assertion number 4 in the scenario. Now, we've got a critique of that, of course, and it's very similar to the critique of assertion 3. It's again an epistemology ontology problem.
Okay, and before you add this critique,
Yeah.
you might say it's a double critique because the first one still stands.
Yes, it does.
Okay.
It stands. Yeah, we really can't just say that the universe is actually small because we no longer have a way of measuring length. Okay?
Got it. But if we were to say, let's concede for the sake of scenario that
right,
it's smaller, I have an additional critique.
It follows directly from the other because it's the same type of problem. Okay.
Got it. Okay.
So changing the scale by which one measures length or volume of a space occupied by radiant energy does not change its wavelength or frequency. Okay. It's the same problem. Just because we can't measure it doesn't mean that it's now magically smaller. All right. Or conversely, that the energy is now magically greater. Right. The absence of a physical ruler does not entail the absence of a physical extent in the case of, or a smaller physical extent and greater energy associated with it. Conformal rescaling is an equivalence between of mathematical descriptions. It does not change the entity being described. Okay, so again, this is the ontology epistemology problem. We're confusing our description. Oh, we're going to call it one mountaineering unit. That doesn't change Mount Everest. It only changes the way we're describing it or the way we're going to or the measuring scale that we might apply to it or not apply, okay? So the same problem that we had with length, we now have with energy, just simply treating the universe as if it's small and then treating the universe as if it had more energy available to do work is it's a sleight of hand, okay? Because we haven't changed anything about the length scale, the length itself, the size of the universe itself, or the energy available to do work within the universe.
So effectively, his model requires this scaling down
Right.
and more energy
And a corresponding increase in energy available to do work.
because it's smaller.
Yeah.
And both of those are not accounted for themselves. We're accounting for measuring them, but a change in measuring doesn't change the energy and the size itself.
Exactly.
Is that fair?
That latter
Okay.
point is exactly the right way to say it.
Okay.
Yeah, that's good. Okay, so again, all of this is confusing our description with the reality of the thing being described.
And we've got the notes and the points here. People can
yeah.
go back and work through. Okay, good.
Yeah, and in this, with the specificity of this critique, of the fourth proposition is if we change the scale by which we measure wavelength, we will not change the actual wavelength and its associated energy. Okay, so that's it's very similar to the critique of proposition 3.
Good.
Okay, now in the PowerPoint we have a nice a couple of slides where we are quoting Sir Roger, showing that we're being accurate.
Being
We're-
careful.
We're respecting the Dylan principle here.
Good.
The Bob
Love
Dylan
it.
principle. Okay.
All right.
Now here's where it gets really interesting. The energy generated by conformal rescaling. Okay. Now in Sir Roger's model provides the basis for a new field, an energy-rich field capable of generating particles with mass called Arabonds. And Arabonds is his own coinage. All right. Now he used to call this a phantom field. And one of the things he critiqued me for in our conversation is I was still calling it a phantom field, but he's gotten rid of that designation, the phantom field. He used to call it a phantom field because the field really had no physical presence or it wasn't activated until it was needed.
Forget the phantom field. There's nothing in the description. Probably did use the term phantom field at one stage, but it doesn't feature in the modern scheme. That's not the term that I would use now. There's no such thing as a phantom field in the scheme.
It was kind of ghost-like. I in our conversation said that's sort of imputing to a physical field properties of mind that no known physical field has, okay? But he's adjusted his model a little bit now, and he says that we got this energy available to do work. It creates a field that creates particles or they're called Arabonds.
And this is assertion 5.
This is
we're on to
assertion 5 now.
Okay.
We're into assertion 5. Okay. So he's since retired the name of phantom field, but now he claims we've got this field that can create Arabonds. And these Arabonds, he further proposes only interact with a gravitational field and that they eventually, near the end of the eon, will decay into gravitons.
It needs a better theory than that. It needs a theory which explains in detail why this happens. I'm just giving you the overall picture, which is incomplete at the moment, I agree. It needs more calculation. It needs how to describe the Arabonds properly in the theory, why they decay into gravitons, into a pair of gravitons, would be the argument, and why do those gravitons survive until the next eon, and then things are the other way around. They start to collide again and produce more Arabonds. So the Arabonds come back as the gravitons start to run into each other, and as in the highly hot, dense new universe, it's enough gravitons running around hitting each other in a certain sense. I mean, it's hard for gravitons to hit each other, but there is an amplitude, if you like, for the graviton to make an Arabond.
Now, part of the critique here is that no known particle possesses these properties. So whereas before he had a field that had that corresponded to the properties, he had a field for which that had properties that had no precedent in other physical fields. Now he's got particles that have properties that are not similar to any known particles. Okay. Well, again, we've got a nice quote from Sir Roger about the universe at crossover, how it's important that we get a huge amount of new matter. Now, we got rid of the matter. This is what he's trying to achieve. He got rid of the matter to do the rescaling, but now to get a universe that's going to expand and form galaxies, you got to have matter again. So the new energy-rich field produced by the low entropy state with lots of energy available to do work is going to produce these Arabonds that are eventually going to they're actually going to be the dark matter, but they'll be part of the equation of they'll be part of the situation as the universe begins to expand again.
Okay, so this is not like the steady state theory where matter is coming into existence, so to speak, that didn't exist before. Is this a shift in state?
Yeah, good question. It's the matter is going to arise in the new eon as a result of the energy that's available to do work and concentrated and present in this new field. Okay. And that matter now, and this is his crucial next move, and this is the last assertion. Okay. The last part of the scenario. At the crossover event, Penrose assumes rather than derives a near perfect uniformity of the gravitational field. Okay, so that's a kind of fine-tuning that he's going to introduce.
I have no idea what he's talking about. There isn't any fine-tuning of this sort. The main material in the universe is dark matter, and the dark matter comes about through gravitons. And it's not a question of any fine-tuning. There isn't any fine-tuning in. I don't know what he's talking about.
He doesn't call it fine-tuning, but he assumes a near perfect uniformity in the gravitational field. It's something called zero Weyl curvature, all right, in physics terminology. He then asserts that the Arabond-producing field generates the right number of Arabonds with the right collective mass so that as the universe expands, they are perfectly balancing the cosmological constant, which is active in every one of his eons. That's a constant. It's continuing this outward push. But now he wants new matter to be introduced so that it doesn't expand too quickly and we get a new dissipation of mass energy. Instead, he wants the universe to be expanding at the right, somewhat sedate pace so we can get galaxy formation. So we've got to have the right number of Arabonds with the right amount of combined mass to generate just the right amount of gravitational attraction to counter the outward push of the cosmological constant. So he's got a very beautifully, finely tuned system in mind. Okay, and that gravitational attraction will counter the cosmological constant, the other forces responsible for the initial rate of expansion, so that galaxies can form. Okay. So it's fine-tuned for galaxy formation. So
can I jump in for
yes,
clarification?
Okay.
If this is too simplistic, just say it's too simplistic. One of the critiques I've heard of the oscillating universe
Right.
is not only that it needs more energy, but that each expansion and contraction would need to be fine-tuned with something like, say, a cosmological constant.
Yeah.
That's a critique of that model. It sounds like there's at least similar critique, even though his model is very different than oscillating, requires some fine-tuning.
And this is what we're finding and time again with all these new infinite universe cosmologies. This is illustrative of a pervasive problem. Going back to, this is why I cited the Einstein
example.
Okay. And in my debate with Phil Halper, I started to explain that, and the debate was very skillfully moderated by Justin Brierley.
The best.
Yes, but I wasn't able to really unpack that example to illustrate, I think, as we're doing now, how incorrigible, pervasive this need for fine tuning is in these infinite universe cosmological models. There's always a cost. Okay, and right now we're seeing. I'm going to summarize the cost, but one of the costs is going to be.
Okay, so hold the thought before
a whole lot of new fine tuning. Okay.
Okay,
yeah.
new fine tuning. Sorry, I didn't mean to cut you off. I want to make sure people understand this 2 to 3 hour friendly debate with Halperin is on Justin Brierley's podcast.
Yeah, Phil Halper is
Halper, thank you.
Right.
Around the same time, we released this intentionally around that time so people could watch both, push the conversation forward.
Absolutely.
But if people are going, wait a minute, we want some pushback from a skeptic, watch that longer dialogue.
Yeah, Phil and his co-author, Professor F. Shorty, have written this new book called Battle for the Big Bang, and they do a wonderful job of exposition of these new models. They have about 25 in there. Bruce Gordon and I, working on this with our colleague Brian Miller at Discovery Institute, we've actually found 41 models, and we're writing up critiques of all of them. And
Good.
We're writing up a generalized critique that applies
across the board.
All of them. There's just the proliferation of these things is kind of like rabbits. But
so keep us posted when you have all those. Here, let's move.
This discussion of Sir Roger's model is very is illustrative of common problems with all these models, and it is an. I found this pattern first in critiquing what's called quantum cosmology. And that critique is in chapters 17 and 18 of Return of the God hypothesis. And that's where I developed this idea that the pick your poison, either way, naturalism has a problem kind of argument. Philosophers call that a robust argument, where you get to the same conclusion irrespective of two or more different factual predicates, where you start with different set of facts, but you end up the same conclusion either way. And the different facts are the universe was finite, which I think is what is overwhelmingly supported by the evidence. The other factual predicate would be no, it's infinite. It is infinitely old. But even if you start with that predicate, you end up with a theistic conclusion.
Okay, good.
So this is what we're and we talked, I think, in the previous conversation that's where I felt I had been misrepresented. Phil has been put out a video saying Meyer is wedded to a singularity-based apologetics.
Removing the singularity unsettled those who had built theological arguments based on this notion that physics breaks down at the Big Bang. And unsurprisingly, intelligent design advocates like Stephen Meyer, in his recent best-selling book, have attacked Hawking's work. But as we'll show, these attacks miss the mark.
The singularity refers to the singularity theorem of Hawking and Penrose. And I very carefully explained that the singularity theorem does not provide an absolute proof of the beginning, but I think it points decisively in that direction, that if we combine general relativity with our understanding from observational astronomy of the expansion of the universe, it's giving us a picture in the reverse direction of time of the universe is getting smaller and smaller and smaller, and spatial curvature getting tighter and tighter and tighter, and it's approaching almost asymptotically a limiting case where you can't go back any further. There's a way to get around that. When you get small enough, we can't close it right to the final singularity. But that's where quantum cosmology comes in, and then I show that quantum cosmology itself has theistic implications. So if you want to get around, I think there's a strong pointer to a beginning, we rarely expect absolute proof in science to come to a
of
conclusion.
course,
I think the postulation of a beginning provides the best overall explanation of the observational astronomy and the results from theoretical physics, but we don't have an absolute proof of it. I concede that, but then say if you want to you want to develop these models to give us a picture of an infinite universe, you're going to have other problems if you're a philosophical naturalist.
Makes sense.
Yeah. Okay, so assertion 6 was you've got to have this energy-rich producing field generating the right number of Arabonds with the right collective mass to essentially slow down that cosmic expansion so you get things balanced right to make galaxies. So absent such fine-tuning, the universe in the new phase of expansion would either collapse back onto itself in a big crunch or expand too rapidly, and we get the heat death problem, okay? So clearly, Penrose's model is introducing extensive new sources of unexplained fine-tuning, thus providing additional basis for a theistic argument. Fine-tuning pointing to a fine-tuner.
Yep.
So now just in summary, to draft the whole thing up.
Do it.
This is our idea that, yes, you can model your way out of the beginning, but only at a very high epistemic cost, and especially at a high cost to philosophical materialism or philosophical naturalism. First of all, you have violations of established physics. Asserting that, and I'm going to enumerate them now in summary.
Do it.
Asserting that black hole evaporation ultimately reduces entropy contradicts what's called the unitary principle of quantum mechanics. So that's a big deal to contradict that. Now, there are physicists who agree with Penrose. I kind of see some of his rationale on this, but overall, to assert what he's asserting about the loss of information and the reduction of information of the whole universe, it does run counter to very established physics.
Okay.
The claim that all ordinary matter will convert into radiation, that was his second proposition, has no basis in the standard model of particle physics or nor in any known physical phenomenon. So that's a pure kind of postulation that's at least not has no basis and maybe even is contradictory to some of the things we know in physics. The mathematical sleight of hand is the whole idea that that a change in the measurement scale can be will result in a change in both the length and the energy of the entity, i.e. the universe, being measured. Okay, so that's the ontology, epistemology confusion. More problems. Ad hoc postulations or violations of Occam's razor. Remember, Occam's razor says all of the things being equal, we want to avoid needlessly postulating new theoretical entities. Okay, don't postulate additional theoretical entities as much as possible. Avoid that. So he's got a number of new theoretical entities, new things for which we have no precedent. They're purely ad hoc. First is his mass fade-out hypothesis, the idea that all mass in the universe will be converted into radiation. That's not only inconsistent with known physics, it then is a kind of ad hoc postulation. We're just going to say that this happens. The existence of Arabond-producing fields. In other words, fields that can produce these particles that have properties that no other known particles have. In particular, the properties of Arabonds, the ability of massive particles to decay into gravitons. That's a purely ad hoc postulation. And then finally, we get to what for us is the key thing, and that is the two sources of unexplained fine-tuning. The idea of a perfectly uniform gravitational field, what's called zero Weyl curvature, and then the fine-tuning of the number of and the collective mass of the Arabonds, so that we do indeed get stable galaxies rather than gravitational recollapse or heat death of the universe. So that's each of those four problems. Contradictions of known physics, mathematical sleights of hand, violations of Occam's razor, and postulations of unexplained fine-tuning are characteristics in some combination of all the models that we've looked at.
That's interesting. When you say all, like all 41.
Well, we haven't gone through all 41 yet,
okay.
but we've been looking at the most popular models within physics where this infinite unit, quantum cosmology is one of those, okay? And that's where I first got turned on to this. But you find it in the Steinhardt model, you find it in the book. They propose suspending the limitation on the speed of light, which is a fundamental part of special relativity.
Yeah.
I think they also propose the idea that causality is not a pervasive feature of the universe. Well, you start suspending very fundamental things like that, you can prove almost anything. Well, not prove, you can formulate a consistent model, but the cost is very high. That's the idea. Either to coherency of the physics or plausibility of the math, or especially the cost is very high with respect to the need to postulate new unexplained fine-tuning, and therefore thereby providing alternative support for a theistic argument, an argument for theism, the argument for theistic design based on fine-tuning.
Okay, so let me take a step back. Some of this, in all honesty, is above my pay grade, but I tracked with your point. I think you made it very well and very clearly. It seems like your critique is rooted in not saying, well, I'm an outsider from the scientific community and I'm going to quibble with these small points. You're saying physicists, whether they've pieced it all together and applied it to the Penrose model, would agree with the challenges. These are pretty standard critiques that you're making.
There are many other physicists that have critiqued the conformal cyclic cosmology. In the PowerPoint that we'll provide to your viewers, I have several extended quotes from people, prominent physicists, critiquing this. At one point, Professor Penrose, in his very self-effacing way, described his model as the conformal crazy cosmology. Okay, so he's aware that this is a bit of a walk on the wild side. And when I debated Phil Halper, and I would critique specific models, he would say, well, we're not saying this model is right. We're just saying that it's a possibility. The very fact that there's so many that are possible means we can't say that there was, in fact, a beginning. Our counter-argument to that is that because of these pervasive these pervasive problems that we find in all the models that we've examined, that simply, throwing a whole bunch of mud at the wall and hoping it sticks doesn't mean that's an effective strategy. The standard hot Big Bang model that explains, that's so powerfully suggested by the evidence for the expanding universe, by the cosmic background radiation, by so many other empirical results, and by the proofs that come out of theoretical physics, the singularity theorems, which don't absolutely prove a beginning, but point decisively toward one. And I think an even more compelling proof, the Borde-Guth-Vilenkin theorem, which, again, like all proofs, is predicated on certain assumptions.
Yep.
Okay, everything is predicated on postulates or assumptions, but they are fewer. They don't require meeting the same energy conditions that the singularity theorem does. The only assumption that's necessary is that you for any universe which is on average expanding, they show that there must have been a finite beginning. And so that's based on special relativity, not general relativity. It's not subject to the problem of getting inside the Planck time, and then you have the quantum effects becoming dominant. You don't have to worry about that in this other proof. So there's a number of very powerful indicators of a beginning. So I think the best overall explanation of our cosmological history is that there was a beginning. But I acknowledge that there are these other models, that every proof has preconditions, and that if you want to suspend those or challenge those, you can model your way out. But then you have this big epistemic cost, and it leads you right back to theism.
So we have about 4 or 5 minutes at most.
Yeah.
What would critics have to do to respond to, say, your model or strengthen Penrose's? And where do you see this going from here?
I think what we're proposing is not so much a model, but a framework for understanding.
Okay.
And saying, look, we're wrapping a framing around this that says, either way you go philosophical materialist or naturalist, you've got trouble for your metaphysical belief system. The evidence for the beginning, I think, is best explained by the postulation of something like a theistic or deistic creator. But if you don't, if you want to say you don't like that beginning, and we're going to go back to an infinite universe cosmology, then likely you've got something that's got a fair amount of incoherence to it, that's contradicting a lot of known physics. But even if you set that aside, you invariably have to have a system that's very intricately finely tuned, and then you're back to an argument from contingency or a fine-tuning design argument. So, and I think to refute what we're saying, people are going to have to show that they can develop an infinite universe cosmological model that doesn't come at the high epistemic cost that we are saying is inherent to the enterprise.
Gotcha. That makes sense. One of the critiques of intelligent design is that it doesn't make predictions and it's not testable. You have 41 models. You've seen this pattern show up again and again and again, and also see it in your critique of Penrose. Is it a prediction that as we work through the rest of these 41 models, you will see
they're going to have one
similar...
or more of these problems? Yeah.
Okay.
Yeah.
All right. Well said. Well, as you work through those, maybe when you get through the 41 to get closer, we will have you back to take a look and kind of assess us on where this discussion and this debate is. Sir Roger Penrose, if you happen to see this, we would love to get a response from you. We'd love to have a conversation with the two of you, and it wouldn't have to be a debate, just clarifying and getting your sense on...
And I would say too, just in all modesty here, this is one of the great scientists of the 20th century, 21st century. I have tremendous respect for him. And if I got something wrong, I'd love to have that clarified. The whole reason we did this is that there were a few things I got wrong. In fact, I failed to mention one of them was about the picture, okay, the idea of the universe coming out of the patch. I also misstated the name of the theory. There were a couple other things in the way I described his views about entropy that we've tidied up in just this presentation. But the central critique about the unexplained fine-tuning, which he objected to, because I don't think I think this happens a lot in all kinds of simulations, both in prebiotic simulations of origin of life and also cosmological simulations of the origin of the universe. Often the theoretician forgets what they themselves are adding to the model. That
makes sense.
Yeah, and so I think this is clearly he's postulating the need for unexplained fine-tuning. So I think that part of the critique holds. But I very much welcome the opportunity to improve my own understanding of this. These papers are hard. And you have to really go through them carefully to make sure you're getting it right. And I've got a good group. We have a good physics and philosophy of physics research group at Discovery, and several of us really carefully combed this stuff. And if there's further need for refinement in our understanding, we want to make sure that's the basis of any further discussion.
Love it. He was willing to sit down with William Lane Craig not long ago, and just a wonderful, insightful, respectful conversation. Something like that with Dr. Stephen Meyer would be wonderful, I think, for people on all sides of this conversation. Thanks for all your work on this. I could tell this took a ton of time and a ton of thought to really clarify and make your case. I think you made it well. I'm going to go back and listen to this myself a few times to make sure it sinks in. I was tracking with the big picture. This might be one that people want to go back through and maybe grab a physicist friend and say, walk through and explain this to me. When you get it, the lights really go on because you made some important responses and critiques. So thanks for coming back on.
Thanks for having me, Sean. A great conversation and a bit of a walk on the wild side, but we got through it.
Loved it.
Yeah.